Welcome to solverfy.
35.32. So we have a double slit experiment, and we're looking at a point P, and the electric field of the waves incident at P look like this, where we've got an amplitude, an angular frequency, and this is offset by a phase. And we want to do some stuff with this. So the first thing is, what is the amplitude of the resultant wave? So here all we have to do is add them together. There's a couple ways you can do that. You can either treat them as phasors, or you can use trigonometric identities, which is what we'll do here. So we have an identity, the sine of A plus the sine of A plus B is equal to 2 times the cosine of B over 2. B is going to be our phase here, times the sine of A plus B over 2. So everything is just multiplied by an E naught. So we have a cosine of the phase difference divided by 2. And then the sine of the same time dependence, and with a phase of phi over 2. So the amplitude then, sorry, I forgot a 2 here. So the amplitude then is just 2 E naught cosine of phi over 2. And just putting in all of our numbers, we find that this is 2.33 microvolts per meter. So it's slightly higher than the original amplitude of both waves. So for part B, we want to know the intensity of at point P divided by the intensity at the center of the screen, or whatever the interference pattern is being projected onto. So if this has some intensity I naught, at point P, it'll have an intensity of 4 times I naught times the cosine squared of our phase divided by 2. And this will have an intensity of 4 times I naught, this being the intensity from one point source, times the cosine squared of 0, which is the phase difference at the maximum, the central maximum. Of course, cosine of 0 is 1. So this works out to be 0.338. So now we want to describe where point P is in the interference pattern, say what maximum or minimum it's at, or which it's between. So the easy way to do that is to look at the phase difference in wavelengths. So if we divide the phase in radians by 2 pi radians per wavelength, we have 39.6 divided by 2 pi, and so this is 6.3 wavelengths. And this lies between the 6th maximum to the side and the 7th minimum. Because every wavelength you have a maximum, and every half wavelength you have a minimum. So, or every like odd half multiple of wavelength. So, now we ask if we have a phasor diagram, what is the rate that the phasors are rotating around at, and what's the angle between them? So the rate is, they both have the same angular frequency, and the angular frequency is exactly, the angular speed of our phasor rotating around as time goes on. So they move around with a frequency of 1.26 times 10 to the 15th radians per second. And then we want to know what the angle between them is. And the, phase difference between two phasors, or between two, functions when they're interpreted as phasors, is the angle between the phasors. So this is just our 39.6 radians. This is about 2,270 degrees, which is equivalent to 110 degrees if you subtract off whole multiples of 360 until you get to something less than 360.